All right, so this brings me to the second half of the chapter, which is based on buffers. Now, we have already seen the importance of aqueous solutions in chapter 15 and in the earlier part of this chapter. And now I'm going to focus on buffers, and then later on, we are also going to talk about the pH metric titrations, use of a pH meter, how we run the math, etc. So, first things first, what is a buffer? Um, so for that, I kind of come back to the same question that we asked earlier about calculating the pH of a solution prepared by dissolving 0.10 moles of acetic acid and 0.10 moles of sodium acetate in water, and then diluting the solution to a volume of 1 liter. So how do we solve this? First off, uh, I would like you to think about just acetic acid on its own, CH3COOH, just for a second. If that is put in water, and that's going to give you acetate, and it's going to give you hydronium ion. Hopefully you can see that if you knew the concentration of hydronium ion, you would be able to determine the pH of the solution. So if you were to set up an ice problem, you will say initial concentration of acetic acid is 0.1. Of course, acetate as well as hydronium are 0. But if X moles of acetic acid go through the ionization, X of acetate, X of hydronium will get generated. And hence at equilibrium, zero point 0.1 minus X will remain. X of acetate will remain, X of hydronium will remain. So if you were to set this for a Ka, you would say concentration of acetate times concentration of hydronium divided by acetic acid should do the trick. And now I'm going to just substitute the values. Acetate is X times hydronium is X as well. Acetic acid is 0.1 minus X, and that is coming out to be 1.7 times 10 to the power of minus 5. So now you have to ask yourself whether you can use an approximation or not. By all means, what you can use quadratic equation, but it's kind of pointless to do that because approximations work all the time. So again, we are going to choose the concentration, which is 0.1 moles of acetic acid, and it's 1 liter, so it will be 0.1. And I'm going to divide that by the value of Ka and see if that number is going to be greater than 100 or not. And just by eyeball, you can plug this on your calculator, but I can see this is 10 to the power of minus 1. And this is 10 to the power of minus 5. So this is to the tune of somewhere around, 5,000, 6,000. That's a pretty high number. And so we will say that approximation is true. And if the approximation is true, we can say that 0.1 minus X is approximately equal to 0.1. And so one can say X squared divided by 0.1 is equal to 1.7 times 10 to the negative fifth, or X is equal to 1.7 times 10 to the negative sixth square root of that. All I have done here is I have multiplied both sides of the equation by 0.1 and then taken a square root of both sides. I'm just going to do a ballpark because I know that 1.69 square root of that will be 1.3. So this is going to be 1.3-ish times 10 to the power of minus 3 molar. And what was X? X, by the way, was the hydronium ion. So if I take the negative log of this number, I should get my pH. So let's do that. Negative log of this number, 1.3 times 10 to the negative 3. That comes out to be 2.88. That is your pH. So what I know so far is that if I take acetic acid and I take 0.1 moles of it, so this is acetic acid alone, nothing else. So I have a beaker. In that I put acetic acid. I just took 0.1 moles of it and I filled it all the way to the 1 liter mark. That is going to have a pH of 2.88. Now I'm going to set up a concoction. So it's no longer going to be just acetic acid. It's going to be a mixture of acetic acid and sodium acetate. Two things are going to happen. Let me make some room for that calculation. So it's a mixture of sodium acetate and acetic acid. What does that mean? That means that, of course, my acid ionization is going to take place. So acetic acid with water is going to give you acetate and hydronium ion. But we also have sodium acetate. And sodium acetate is like sodium chloride, for that matter. It's a salt. So the moment you put it in water, it spontaneously will completely ionize to give you acetate and sodium. That means if you begin with 0.1 moles, it is going to give you 0.1 moles of the acetate. What does that tell you? That tells you that you actually are beginning with zero point 0.1 moles of acetate within that beaker. That means how have we generated the solution? We have added 0.1 moles of acetic acid, Ch3COOH. We took 0.1 moles of sodium acetate and we are filling it up to 1 liter water. That's what we have done. That means I already have my acetate. The source is different. The source is sodium acetate, but it's there. Molecules, realize, do not have eyes. They don't know what the source is going to be. All we are saying is that initially there is some acetate that is present in the system. And so hopefully you can see that while change is going to be exactly the same, equilibrium value will look like 0.1 plus x for the case of acetate. And so if you had to plug numbers in, it's going to look like 0.1 plus x times x divided by 0.1 minus x. And again, you have to ask how small is x, so whether the approximation holds true or not. And again, the concentrations are 0.1, so for the reasons we worked on before, 0.1 plus x is going to be about equal to 0.1. 0.1 minus x is going to be about equal to 0.1 as well. And you can say that your equation boils down to 0.1 times x divided by 0.1 equal to 1.7 times 10 to the power of negative 5. 0.1 and 0.1 cancel off, and the value of x comes out to be 1.7 times 10 to the negative 5th. And when you take a negative log of this, that will give you pH. So if you try to take a negative log of 1.7 times 10 to the negative 5th, that value comes out to be 4.78 on my calculator. We were at 2.88. We got 4.78. Realize, if you would have added sodium acetate, that means you would have pumped in the acetate concentration. Don't you think that the backward reaction would have proceeded, which basically means that the amount of hydronium would decrease or the pH would increase? And that's what we see, that acetic acid by itself was 2.88. In presence of sodium acetate, the pH rises. We proved our point. There is nothing but something that resists pH change. So buffers resist pH change. So you might wonder, how is it that they're going to do that? First off, buffers are important first and foremost, and I'm going to get into how they do that. But why are buffers important? They are tremendously important, especially in biology, because all physiological processes, they occur usually within a narrow pH range. For example, for us, our best performance is seen when the pH is between 7.24 to 7.40. That's a pretty narrow range. It's only 0.16 pH unit. And so it's important to maintain that pH. Any pH lower than that or any pH higher than that can lead to a condition called as acidosis or alkalinosis, which essentially refers to greater amount of hydronium ion or greater amount of hydroxide. That means the buffer, in our case, blood being the buffer, has gotten disturbed somehow. And so sometimes a drastic change in the pH could be even fatal. So you can have symptoms like dizziness and shortness of breath, unconsciousness, and in the worst scenario, it can even be fatal. And so maintaining that buffer for the proper functioning of the ecological system is of utmost importance. It is really important. So to give you a flavor, let's consider the antifreeze ethylene glycol. Ethylene glycol, the structure of that is this compound, and you can perhaps envision that this would be very soluble in water because it has the capacity to form hydrogen bonds at the OH. Now, this is something, if you are wondering, we have talked about this though previously, as to where we use this. This is used in your car radiator in the coolant, and it's used as an antifreeze in the cars as an aqueous solution of ethylene glycol. And so it does have a somewhat sweet taste, and so it can attract, small pets or even young children who could be vulnerable to this toxic compound. Now, the first stage of this glycol poisoning resembles like a state of drunkenness, and um, later on, if left untreated, essentially this could lead to more problems. Now, how does ethylene glycol metabolize? In liver, ethylene glycol gets oxidized into glycolic acid. So one of these OHs gets converted into COOH, and it enters the bloodstream. Realize this is a carboxylic acid, so this is acidic, and this is going to drop the pH of the blood if the blood were not a buffer. So depending on the amount of the glycolic acid that you have, realize that blood itself is under a very tight, while ecologically, physiologically, most of our cells are between 7.24 to 7.40. Blood is between 7.36 to 7.42. So it's tighter. And many proteins essentially require this narrow pH range for their proper functioning. And if this glycolic acid enters the bloodstream, essentially there can be a problem, because if the concentration of glycolic acid is too much, then the buffer may not be able to resist that pH change. Realize that you have H2CO3 carbonic acid, which in presence of base would give you water and bicarbonate. And this bicarbonate is going to neutralize the protons provided by the glycolic acid, the H plus, to give you H2CO3 back. So in this way, the carbonic acid bicarbonate buffering system keeps the pH blood or pH of the blood constant. Now, if the concentration, like I was saying, if that concentration of glycolic acid becomes too much, then the blood pH is going to drop dangerously low, and that kind of situation would be called as acidosis, and this is going to affect the ability of hemoglobin, for instance, to be able to carry oxygen. So just to give you a flavor, hemoglobin uh, in the protonated form picks up the oxygen and carries oxygen while it delivers the proton off. Now we are saying that glycolic acid is present in the system. That means we are able to pump in protons into the system. And so according to the Le Chatelier principle, hopefully you can see that a backward reaction will be more pronounced. That means the ability of hemoglobin to pick up oxygen is going to be diminished. And so if that is the situation, then your pet or the child would be hyper ventilating in an effort to overcome this acidic blood's lowered oxygen carrying capacity, and if left untreated, the results of the situation could be really bad. And so to the extent that it could be fatal. One treatment for ethylene glycol poisoning is the administration of ethyl alcohol. Ethyl alcohol is essentially your wine, what is present in any alcoholic beverage for that matter. The two molecules are similar. The only difference between the two is that one contains only one single OH, the other contains two hydroxyl groups. But the way the two are metabolized is pretty different. So essentially, the liver enzyme is going to, P450 is going to work on ethanol as well, but it's going to generate, either it's going to go through the body unmetabolized, or it's going to generate acetic acid, which by the way is also generated naturally in our system. So it's not going to be, it's going to be excreted through the urine, and we are not going to see these kind of effects that we see for the case of the glycolic acid generated from ethylene glycol. So again, I gave you the entire story about buffers, gave you an instance of that to make you understand that buffers, the primary reason for that is, for the existence of buffers in nature, is to resist pH change, because essentially nature would want to protect itself as much as it can. Now, you might ask, what does the buffer contain, and how does the buffering action take place? And like I said earlier, a buffer contains a weak acid and its conjugate base, or it could contain a weak base and its conjugate acid. So either it will contain a weak acid with its conjugate base, or it would contain a weak base with the conjugate acid. Both of those can act as buffers. For example, in the previous slide, I gave you a situation where I had carbonic acid, H2CO3, and I removed the proton and gave you bicarbonate. So that's one buffer, right? So that's the weak acid. That's the conjugate base associated with it. You could have ammonia with ammonium, where ammonia is your weak base and ammonium is your conjugate acid. So a weak acid by itself, even though it partially ionizes to form some of the conjugate base, does not contain sufficient base to behave itself like a buffer. Similarly, a weak base by itself, even though it partially ionizes water to form some of the conjugate acid, doesn't contain sufficient amount of acid to behave like a buffer. That means a buffer should contain significant amount of both a weak acid as well as a conjugate base. But I just said again, just to give you a flavor, because we have seen both of those reactions previously. Let's say you have HF. Okay, when you put HF in water, you're going to get a little bit of hydronium ion, and you're going to get F minus. But it's not like 100% dissociation because it's a weak acid, right? So my HF F minus system doesn't necessarily have like a boatload amount of F minus. Likewise, if you consider the backward reaction or the fact that fluorides generate a slightly alkaline solution. So if you put that in water, it's going to rip off the proton and will give you HF and OH negative back, right? So F minus is giving you HF, but it's not enough, it's not sufficient. So based on those two reactions that we have seen in the past, realize that HF on its own cannot behave like a buffer because it doesn't have significant amount of F minus ion. It's not a complete ionization, that's right. And the other is that F minus on its own, so sodium fluoride on its own, for instance, is not going to generate enough amount of HF for that matter. And so for that reason, neither the conjugate base by itself nor the weak acid by itself can behave as buffers, but the two together are included to form a buffer. So a buffer must contain significant amounts of the weak acid and the conjugate base are desired. So concentration is a big thing. Okay? All right. Now, suppose you add like a strong base such as sodium hydroxide. Okay, that's a strong base which undergoes complete ionization. And I put it in acetic acid. So I have acetic acid, Ch3COOH, and I have sodium hydroxide, and I put the two together. You will say that acetic acid will neutralize the base, so it will generate CH3COONA, and H2O will be generated as the byproduct. So one can say that as long as the amount of the added sodium hydroxide is less than the amount of acetic acid in terms of moles, then the buffer is going to be able to neutralize that. So since we know that acetic acid is going to neutralize the acid, the alkaline part, if this acetic acid is a part of a buffer, so let's say now it's part of a buffer, CH3COOH, and you add the sodium acetate, they are together. If you add a little bit of sodium hydroxide, as long as the moles of sodium hydroxide are less than the moles of acetic acid, essentially that acetic acid should be able to neutralize the added sodium hydroxide. And likewise, if you add HCl to the system, so suppose you added HCl to the system, as long as the moles are going to be less than the moles of the base, which in this case is going to be sodium acetate, because that sodium acetate will react with HCl to give you acetic acid and Cl negative. So with acetate, you're going to get acetic acid and Cl negative. So if it was sodium acetate, that will become NaCl in that case. So realize that as long as the number of moles that are being added are less than the moles or the concentration of the acid part and the base part of the buffer, we would be able to resist pH change. That means whatever change occurs, it's going to be minimal. That's why we say that resistance in the pH will occur. On the other hand, if you just add too much of the acid or the base, then of course the buffer won't be able to withstand that, and hence, in that case, there'll be a problem anyways. So just to again summarize, buffers will resist pH change. Buffers contain significant amounts of both a weak acid and the conjugate base, and the weak acid neutralizes the added base, while the conjugate base neutralizes the added acid. So let's take a look how we can generate a buffer. And when the two are mixed, essentially the starting point is, how does that change the pH of the solution anyway? So let's take a look at that first. So the solution that is a weak acid and the conjugate base mixture, and which resists a drastic pH change, is what is called as buffer. Small amounts of hydroxide are going to resist, they're going to increase the pH by a little bit, tad bit, but not by much. So let's say the buffer was like 4.78, it might become like 4.80 or 4.81, but it's not going to become 6. All right, and this is because the acid component of the buffer would be able to neutralize the OH for the reasons I explained previously. Likewise, realize that if you would add hydronium ion source, so if you add some kind of an acid, it's going to again decrease the pH, but not by much, because the conjugate base component of the buffer is going to neutralize the added hydronium ion. So that is the reason why you need to have a significant amount of acid and a significant amount of the conjugate base in that buffer solution. That concentration is really, really. So just to give you a flavor, some examples: acetic acid and acetate, HF with F negative, ammonium ammonia. We talked about this in class as well. Realize we would not be able to get a buffer of HBr, Br negative, or maybe HCl, Cl negative. These are not buffers, no. And if you can think of a suitable reason, that reason is that HBr is going to completely dissociate and give you 100% proton and 100% Br negative, the conjugate base. It's too much. There is no acid component left there. All it contains is the conjugate base. So that is the reason why you're not going to be able to use a strong acid for the buffer. It has to be a weak base or weak acid and its conjugate version. And like we've already discussed, I gave you the example as well. Buffers are very important in biological system for proper protein functioning, because proteins, hopefully you know this from a biology class, proteins ultimately depend on their structure, the way they fold, for their functioning as well. And if a protein misfolds, or let's say a particular nitrogen atom undergoes protonation, let's say because of the presence of the added acid, a protein may not be able to fold the way it's supposed to, so it might lose its shape. And if it loses its shape, it probably will also lose its function. So the shape is vital for the functioning of a protein. Now, I'm going to go over, more math problems. I'm going to give you the logical way, and I'm also going to give you the easier way. We are going to take a look at both of those and go with that. I'm going to work on one, and I expect you to work on the other, following the steps so that both of us know how to go about it. All right, the question is addition of hydroxide to a buffer. So if what happens if we add 0.01 moles of solid NaOH to 1 liter of the buffer? So the buffer is already there, and we have added a little bit of the base. Okay, so how do we go about it? That's what we are going to discuss next. Now, what I want you to do is I want you to think about what kind of equilibriums do we have in this buffer. So we have sodium acetate, I said, sodium acetate, which was put in water. That means it gives you so acetate and sodium. And we had taken 0.1, that means acetate is present up to 0.1 molar solution. We took acetic acid. So that's my main ionization, acetic acid plus H2O, giving you hydronium and acetate. And essentially, acetic acid concentration is 0.1 initial concentration. And of course, we are going to use the remainder from what's going on in that solution. We are saying that we have added a tad bit, we have added a little bit of sodium hydroxide, solid sodium hydroxide to this buffer. The amount that we added was 0.01. What does sodium hydroxide do in AOH? It completely ionizes. It will provide you OH negative and Na plus. How much OH negative would it provide? 0.01. And that OH negative is going to basically react with the acetic acid component of the buffer. And so hopefully you can see a third reaction is going to take place, that the acetic acid, because realize my buffer is CH3COOH and CH3COO minus. So what's going to happen is that this added OH negative is going to react with the acid part, not the conjugate base, but the acid part of the buffer. So CH3COOH is going to react with the OH negative and give you what? It will give you water and acetate. One might ask, how much of acetic acid would react? Well, realize the stoichiometry is 1 to 1. That means if I have 0.01 moles of the hydroxide, 0.01 moles of acetic acid would have reacted, and 0.01 moles of acetate would have gotten generated. What does that mean? That means that if you have to set up your ice, you began with 0.1 molar solution of acetic acid, but part of it has reacted. So you must subtract that from your initial concentration. Hydronium, of course, is still 0. Acetate, you have 0.1 from sodium acetate, but you have also formed a tad bit from this reaction in red. So you must add that 0.01 to this acetate. Of course, the change is going to be the same way. And so your overall reaction is going to be 0.09 minus X at equilibrium, X for the case of hydronium, and 0.11 plus X for the case of acetate. And now if you use these numbers to plug in for your Ka, your Ka will start looking like hydronium, which is X, times acetate, which is 0.11 plus X, divided by 0.09 minus X. Again, you ask yourself if you can use the approximation or not. So the concentration of acetic acid is 0.1. The Ka value is 1.7 or 1.8 times 10 to the negative fifth, which is way more than 100. The approximation is valid, and so you can neglect the value of X and you can rewrite this as 1.8 times 10 to the negative fifth is equal to X times 0.11 divided by 0.09. And now we are going to solve. As we solve, X will come out to be 1.47 times 10 to the power of negative fifth molar, and X is nothing but the hydronium ion concentration. So if you take the negative log of this number, 1.47 times 10 to the negative fifth, that's going to give you a value of 4.83. Recall, your pH of the buffer was 4.78. pH of the buffer was 4.78, and it only rose up to 4.83 in spite of adding the 0.01 moles of the base. I want to just give you a scenario just to kind of, make you realize what this resistance to pH is. Right now we are saying the change in the pH, it has increased, yes, because you added buffer, but the increase is very, very little. It's only 0.05 units. That's nothing. Compare this to a situation, what would have happened if you would have 0.01 moles of sodium hydroxide to distilled water. Distilled water. Distilled water, the pH of neutral water is 7. If you would have added 0.01 moles of NaOH, that means the concentration, and we'll keep it 1 liter. The concentration would have been 0.01 molar. So the pOH, because it's a complete dissociation, the pOH is going to be negative log of 10 to the power of minus 2, which would have been 2, or pH would have been 14 minus 2, which is 12. That means you would have gone from pH 7 to pH 12, a difference of 5 units. And realize that if this is on the negative logarithmic scale, that means the concentration of the hydronium is changing by 100,000 folds. Because as you can perhaps recall from chapter 15, that with every unit change in pH, that basically means that the hydronium ion changes by 1 unit. So that's pretty remarkable. That's pretty significant. So realize that a buffer did not allow a change more than 0.05 units, whereas water, doubly distilled water, or deionized water, that will jump from 7 to 12 because of the absence of buffer in that scenario. Alright, the question here is that we have added hydronium ion to a buffer. It's exactly the same situation. I want you to think about what all has happened. And just to get you started, I would give you the equations, but I really want you to work on the math of this. I have worked the base function for you. I want you to work on the acid function, and obviously there is a reason I want you to work on how to go about the ice problem specifically for this. So realize again, we have 2 things in our buffer. We have acetic acid, which with water is going to give you hydronium plus acetate. That's my main ionization, and I have in my solution, I have sodium acetate, Ch3COO minus Na plus. So if I use 0.1, that is going to give me 0.1 moles of sodium and 0.1 of the acetate, and to that I'm going to now add hydronium. So what would happen if I add hydronium, or H plus? That H plus now is going to react with acetate. So hydronium plus CH3COO negative is going to give you CH3COOH and water. What does that tell you? That tells you that the acetate, because amount of hydronium added is only 0.01, and that's going to completely combine. It's going to get used up by the acetate, which is why it doesn't feature in your initial concentration for the ice. It's going to completely use up, and how much will be used up? 0.01 will be used up to generate 0.01 of acetic acid. So now all you got to do is set up your ice. You have to think about how much acetic acid is present. You were given 0.1 to begin with, but have you generated more acetic acid in the process? Aha, you will add 0.01 in this case. Acetate, you had 0.1 in the system, and since some of it got used up, you're going to subtract that, and of course the rest of it remains exactly the same. So work on the math for that and figure out what the pH of that solution would be. You should see a slight decrease in this case. So starting from 4.78 was the pH of our buffer, you will see a slight decrease. It might drop to like 4.70, 4.69 in that range, roughly, but you're not going to see a dramatic decrease. So I want you to work on the math for that, and we'll go from there. All right, that brings me to the effectiveness of buffer, what is called as buffer range and buffer capacity. Realize that an effective buffer neutralizes small to moderate amounts of the added acid or base, and we saw that in the math problems in the last 2-3 slides. And so realize that if you add too much, then the buffer can be destroyed. So the question is, what are the factors that influence the effectiveness of a buffer? When would a buffer be useful in a sense? And so one can say that the relative amounts of the acid and the conjugate base that you have, and the absolute concentrations of the acid and conjugate base, both of those are important. That means how much of the acid and the base is present in relation to each other, what is the ratio for that, and also how concentrated those are. So in terms of what a buffer capacity would measure, it would basically measure the amount of acid or base that the solution would be able to absorb without a significant change in the pH. And again, it depends on how many moles of the weak acid or the weak base or its conjugate version, the conjugate base or the acid, are present. Higher concentrations would mean that the buffer capacity is going to be higher. Greater is the volume, then too one can say that the buffer capacity is higher. So again, the relative amounts of the weak acid with the conjugate base as well as the absolute values, both of those are going to define the capacity of a buffer. That means how much of the added acid or base can it effectively neutralize. And so one can determine sort of like a range that the buffer is going to work in. So that's what this next section is going to focus on. Now, I think I said that in class as well, that a buffer is most effective when the concentration of the weak acid and the conjugate base, so the acid and the base, when those are equal, that is when the buffer is most effective. So an effective buffer basically means that the resistance will be higher. It will resist pH change. Okay. I want to kind of explore this idea by considering the behavior of some, generic buffer which contains some weak acid, maybe HA, and its conjugate base A minus, for which you have a pKa of maybe 5, and I want to keep the sodium hydroxide which is added to this buffer system. I want to keep that pretty low, similar to what we had done in the previous case. 0.01 is a good number. Moles of sodium hydroxide will be added. But what I want to change is that in one case you have 0.20 moles of the acid and the conjugate base. However, in the other case, I want to change the amount of the conjugate base. So essentially, I want to vary the acid to base ratio in the two solutions. That's what I want to do. So we are going to probe two situations, we are going to add sodium hydroxide, and I'm going to add 0.01 moles of sodium hydroxide to both of those solutions. Both of the solutions contain HA. Both of the solutions also contain the conjugate base A minus. Okay, and in the first one you have equal amounts of the acid and the conjugate base, so you can perhaps envision that you have 0.1 moles of the acid and 0.1 moles of the base, so together they are summing up to 0.2 moles total of both the acid and the base. In the other case, I have a skewed ratio, so I have maybe 0.18 moles of the acid and 0.02 moles of the base. It still adds up to 0.2, but the ratio is skewed. It's not equal concentration. And I want to basically see how it's going to change the overall effectiveness of the buffer. Of course, realize that the added OH minus is going to react with HA, which is the acid component, to give you water and A minus. And if somebody asks you to what extent would this reaction take place, you would say you only have 0.01 of the hydroxide, and so after the reaction has taken place, after the neutralization has occurred, since you originally had 0.1, what's going to remain is going to be 0.1 minus 0.01, and what's going to become of the A minus, since you started with 0.1, you're going to end up with 0.1 plus 0.01. And the pH and pKa are linked together using what is called as Henderson-Hasselbalch equation, or HH equation, according to which pH is equal to pKa plus log of base over acid, and we'll discuss the details in a little bit, but for now consider this equation as is. And if I have to determine the pH of this solution, I would say that the pKa is 5, which was given to me. Base is 0.11, acid is 0.09, and when you work out the value, it comes out to be 5.09. So if you consider the pH of this buffer, essentially you went from 5 to 5.09. That's not a lot of change. So in terms of the change in pH, one would be able to say that they basically went from 5.09 to 5.00 divided by 5.00 times 100, and that comes out to be 1.8%. Now, if you do the same thing for this other buffer that we discussed, exactly the same thing is going to happen. Your added hydroxide is still going to react with the HA, giving you water and A minus, but realize that you start with 0.18 of the HA, and so the added hydroxide is going to take away a little bit of that, so 0.18 minus 0.01 will give you 0.17, while you're going to add to the A minus, giving you 0.03 as your overall anion. And so now if you had to use the Henderson-Hasselbalch again, you're going to get base over the acid, and when you plug in the numbers, 0.03 for the base, 0.02 0.17 for the acid, it comes out to be 4.25. And now if you look at the percentage change in the pH, it went from 4.25 from 4.05 to 4.25. And if you try to figure out the percent, it comes out to be 5%. So realize that the buffer with equal amounts is more resistant to the pH and is an effective buffer. So we basically proved the principle that resistance to pH change is a more effective buffer, and so a buffer becomes less effective as the difference in the relative amounts of the acid and the conjugate base increases. So just as a guideline, you can perhaps keep this in mind, that an effective buffer must have a base to acid or a conjugate base to acid ratio in the range of zero point 0.1 to 10, so plus minus 1 on a logarithm scale. So for a buffer to be reasonably effective, relative concentrations of the acid and the base should not differ by more than a factor of 10. You can keep that in mind as you define the buffer capacity and the buffer range for a given buffer. Okay, let's talk about the Henderson-Hasselbalch equation in a little bit more detail than what we have seen. So Henderson-Hasselbalch equation, sometimes also referred to as the HH equation, is an equation that enables me to find the pH of a buffer solution in a more simplified manner by basically deriving an equation for the equilibrium for the weak acid. So recall, my weak acid HA is interacting with water to give you hydronium plus A minus. This is aqueous. Charges are always aqueous, by the way. Water is the only one that's liquid. And we can write down for such a situation that Ka is equal to hydronium times A minus over HA. Okay. All you got to do is rearrange this. So you can perhaps write down multiplying both sides of the equation, so bs again, both sides, multiply both sides by HA, and you would be able to write Ka times HA is equal to hydronium times A minus, and I'm going to divide both sides by A minus. That would give you Ka times HA divided by A minus is equal to hydronium. Okay, and now we are going to take the negative log of both sides. Negative log of both sides. So that means negative log of Ka minus log of HA over A minus is negative log of hydronium. But what is negative log of hydronium? Aha, that's pH. That's pH. What is negative log of Ka? That's pKa. And you can write this right now, it's acid over base, but that's with the negative sign. If you want to make that negative sign positive, then you will have to make the denominator numerator, numerator denominator. So this equation will boil down to pH is equal to pKa plus log of base over acid. That's how we got that. So it's nothing fancy, it's just basically a simplification of the Ka and a mathematical operation on that. Now, if you make sure that the x is small and the approximation holds true, then you can consider that the equilibrium concentrations of the acid and the conjugate base are going to be identical to the initial concentrations. And so to determine the hydronium for any buffer, you can multiply the Ka by the ratio of the concentration of the acid to the base, and you would be able to determine the hydronium ion concentration from there. What I mean by that is that if you have a solution that is 0.100 molar acetic acid, and you have mixed that with 0.100 molar sodium acetate, then since you know that hydronium is going to be equal to Ka acetic acid over acetate, and so both of these concentrations are 0.1. This is 0.100, that too is 0.100. So one can say that the hydronium ion concentration is going to be equal to Ka in this case scenario. And this was a case scenario where both the acid and the base were exactly equal. What would happen if these were in a ratio, maybe 1:10? That is when, in terms of the Henderson-Hasselbalch, which is pH is equal to pKa plus log of base over acid. So if these were in the ratio 1:10, then you can perhaps envision that you would be reducing the pKa by 1 unit to be able to get the pH. Alternatively, if they were in the ratio 10:1, then you will be increasing the pKa by 1 unit to be able to get the pH for that solution, which is why we say that it's plus minus the buffer capacity essentially, or the range in which the buffer works the best is perfect if it is within plus minus 1 unit for that buffer. Now we did a buffer earlier. We studied CH3COOH, CH3COO minus, where both of these were 0.1 molar, and we had determined mathematically using the ICE method, we had determined the pH to be 4.78, I think was the pH. I want to see if we can apply the Henderson-Hasselbalch to determine the pH of this buffer. So pH is equal to pKa plus log of base over acid. Of course, I will need the pKa of acetic acid, or at least the Ka of acetic acid, which by the way is 1.8 times 10 to the negative fifth. So I can say it's negative log of 1.8 times 10 to the negative fifth plus log of the base here is acetate, so that's 0.1. The acid here is acetic acid, which is 0.1 as well. 0.1. Both of those are going to cancel off, so that's not going to actually count. That's going to be log of 1 is basically 0. So all you got to do is get the log of 1.8 times 10 to the fifth, and that should give you your overall answer. So on my calculator, I am determining minus. So on my calculator, I plugged in the value, and I'm getting 5 minus 0.255. That comes out to be 4.75. So notice ballpark there, they're about the same value for Henderson-Hasselbalch and the equilibrium method. And I think the difference is because then we used 1.78 or 1.7 as against 1.8. So let me try that one more time with 1.7. 1.7. 2. 3 minus 5. Yep, and it does come out to be 4.77 if this is 1.7. Okay, all right. The question is, I want to prepare a buffer solution with a pH of 7 and one with a pH of 9. Which of the following pairs of weak acid conjugate base should I use? So if you want pH of 7, you obviously do not want these pHs. You would want to keep the pKa within the plus minus 1 range. So the first one can be made using the last choice, and if you wanted a pH of 9, then you should stick to the 9.25. So as long as you keep again the plus minus 1 for the range of the buffer, you should be fine. All right. The question is, using the HH equation to calculate the pH of a buffer solution prepared by mixing equal volumes of 0.2 molar bicarbonate and 0.1 molar sodium carbonate. So Ka value is provided to you. You know the HH equation is pH equals to pKa plus log of base over acid. So you have to decide for yourself which part is the base, which part is the acid. So again, go back to chapter 15. The acid would contain the proton. As simple as that. Negative log of 5.6 times 10 to the negative 11 plus log of 0.1 divided by 0.2, which is going to now give you your overall answer. So just plug in the numbers, and when you plug in the values, this part comes out to be 10.25, and log of 0.1 over 0.2 is nothing but half, so that comes out to be negative 0.3010, and when you plug in all the numbers, your final answer comes out to be 9.95 as the overall pH for the solution. Alright, the question now is, give a recipe for preparing sodium bicarbonate and sodium carbonate buffer solution that has a pH of 10.40. Now, we just saw that for bicarbonate carbonate system, the pKa was 10.25. In the last question, I calculated that. So, we are going to use the Henderson-Hasselbalch equation again, plus log of base over acid. This is 10.40, this is 10.25, so you can say that 10.40 minus 10.25 is equal to log of base over acid, which is 0.15 is log of base over acid. And so hopefully you can envision that e to the power of 0.15 is going to give you the ratio in which these must be present. So the base over acid ratio should be, since it's log to the base 10, it's 10 to the power of 0.15, which comes out to be 1.412. So if you can keep the ratio of the bicarbonate and the carbonate, or rather the other way around, carbonate to the bicarbonate, if that ratio can be maintained to 1.42, you would use that to prepare this buffer. So realize, in terms of moles, it really depends on how many liters, like what's the volume that you're seeking. In this case, they did not ask anything, but if you had to make, let's say, 1 liter, then if you're beginning with 1.412 molar solution of carbonate, that would mean that it should be just 1 molar with respect to the bicarbonate. And so if that ratio is maintained, you would have the specific pHs for that system. So just to summarize, what did we learn? We learned about the buffer range. The lowest pH for the effective buffer would be if the pH is pKa minus 1. The highest, that will be the lowest. The highest will be when it is pH is pKa plus 1, so it has to range between plus minus 1 unit, and the effective range for the buffering system is going to be over a ratio of 10 between the conjugate base and the weak acid ratio. So what that means is that if your weak acid has a pKa of 5, then the buffer will have a range of 4 to 6. Remember that. And depending on your system, for instance, if somebody asks you which acid would you choose to combine with sodium salt to make a pH at of, let's say, 4.25 is what you need, and there are several choices that are given to you, just the similar example that you saw in the previous slide. Then you are going to select one which is within the plus minus 1 for that, and you are going to make your selection based off of that.